Hey there guys, it's Dr. Franklin. I'm back again with another tutorial. This is a tutorial for probabilities and samples, the distribution of sample means. From a calculation standpoint, this is a tutorial on how to take a sample mean and transpose it into a z-score. So, the research scenarios discussed so far in the course have focused on a single score. That's right, we focused on taking a raw score out of the sample, converting it into a standard deviation unit or a z-score so that we can make determinations as to how many scores are approximately above it and how many scores are below it. Now, most research samples involve larger samples, and rather than a single score, a sample mean is the focus. So in this presentation, I'll present a procedure for transforming a sample mean into a z-score. Now, some of the information that you've learned in days past still applies here. Z-scores near zero indicates a central representative sample. A z-value beyond +2 or lower than -2 indicates an extreme sample. Now, it's important to take into consideration that we can also use the z-score as it pertains to sample means to find the probability of obtaining a specific sample. Now, without further ado, let me go ahead and introduce to you the formula that we will be utilizing to do just that. So we have a sample mean minus a population mean over something called the standard error of the mean. Let's go ahead and point out what each of these abbreviations and symbols mean. This is a sample mean. This is a population mean. And this is standard error of the mean. Now, in regard to the standard error of the mean, I want you to keep in mind that all of this represents the standard error of the mean. In other words, you won't be taking the population standard deviation and trying to multiply it by the sample mean. Think of this uppercase M as a subscript to this population standard deviation symbol. Okay, all of this is the standard error of the mean. Now, I do want to go ahead and put up the formula for converting a single raw score into a standard deviation unit. And I'll go ahead and put up the formula for converting a raw score into a z-score for a sample as well. And I'm doing this for the purposes of drawing comparisons. So in our z-score formulas for raw scores, in the numerator we have a deviation, and then in our denominator we have the population standard deviation, the average distance that raw score is from the population mean. Same thing applies with our sample formula. We have a deviation in the numerator, and then we have the sample standard deviation. Now, look at how similar these two z-score formulas are to this z-score formula for converting a sample mean into a standardized unit. In the numerator, we have something that resembles a deviation, but it's a bit different. We got a sample mean, and we're having the population mean subtracted from it. And then in our denominator, we have something called the standard error of the mean. The standard error of the mean, folks, is very similar to a population standard deviation, but it differs in that the focus is on the sample mean. So let me write out a definition for the standard error of the mean. It is the average distance that is expected to exist when comparing a sample mean to a population mean. Many of you guys may be wondering, how did the standard error of the mean even come about? Well, in most research scenarios, we don't have access to the population. Let's say we had some intelligence scores, and let's say we had a population mean of 100 and a population standard deviation of 15. Now, if we were to select a sample size of, let's say, 25 individuals and constantly pool 25 individuals from the larger population. So let's say we had n equals 25 here, n equals 25 here. You guys get my drift. Just allow me to fill it in here. Okay, let's say we did this across 6 different iterations. It's very likely that our sample mean is not going to be 100 exactly. Sometimes we may get a sample mean of 95. Sometimes we may get a sample mean of 80. Sometimes we may get a sample mean of 96. Sometimes we may get a sample mean of 100. Spot on, right? Sometimes we could get a sample mean of 101. Sometimes we may get a sample mean of 94. And this is just a hypothetical scenario. We are very likely to get a whole bunch of different sample means. In other words, our sample is not necessarily going to be the equivalent of the population. So the statistic may not be an exact replica of the parameter. The likelihood of these things being off is called sampling error. And stick with me, folks. If we were to pull up to infinity, okay, just sample after sample of 25 individuals and calculate sample means for all of them, we are likely to have sample means all over the place, excuse me. Then if we were to plot those sample means, what will likely occur is that we will get a normal distribution of sorts. Okay, and you can imagine that the frequency would be on the y-axis and the sample means would be plotted down here, right? So if we were to plot all of these sample means, and let's say we had x-axis down here, and it spanned from 80 to, say, 110. And these, of course, were the frequencies of the times where it showed up. We would likely get something that resembled a normal curve. This type of distribution would be something called a sampling distribution of means, and in the center it would be expected that the population mean would reside. Get into my point, folks. Stick with me. Now, the average variation or the average distance that we would expect a sample mean, these, to be away from the population mean is the standard error of the mean. Okay, and we would expect that the sampling distribution of means would approximate a normal distribution as samples were drawn up to infinity, as long as there were 30 or more participants in a sample and the population at large was normal. So in other words, if the intelligence scores for this particular population was normal, then it's a high likelihood that the sampling distribution of means will be normal. Okay, so a lot of scribbling there, but all of that was provided as a means of discussing the standard error of the mean and how it comes about. Most researchers are not going to draw samples of a certain size up to infinity, but this has been shown mathematically enough for a theory that is based on the central limit theorem and based on the law of large numbers to be generated. Now, let's get back to our problem at hand. See, I told you guys it wouldn't be that painful. Erase, 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 erase. Or as Boosie would say, wipe me down. I'm just kidding. All I listen to is Kirk Franklin. Okay, so let's say we had a random sample. We're going to work a problem, folks, of n equals 4 scores. And we had a population mean of 20 and a population standard deviation of 4. Say based on this information, we were asked, what is the probability of obtaining a mean greater than m equals 22 for this sample? Okay. So we have n equals 4 scores. We know that the distribution of means may not be normal because that's a really low sample size. We have a population mean of 20, a population standard deviation of 4, and we need to find the probability of obtaining a mean greater than n equals 22. Up here, we have the formula that we need. We have m minus the population mean over the standard error of the mean. Now, I do want to present to you two formulas that you can use to calculate the standard error of the mean. You can utilize this formula, or you can utilize this formula. Based on what we have a population standard deviation. We will be utilizing this formula to calculate the standard error of the mean. So let's go ahead and do that. So we have 4 in the numerator, and in the denominator we have a sample size of 4. You take the square root of 4, we end up with 2. 4 is in the top, and then 4 divided by 2 gives us 2. Next, we can move forward and calculate our z. So we have a sample mean of 22. We're subtracting it from 20, and we will divide by 2. Okay, because 2 is our standard error of the mean. So that will leave us with 2 over 2, and then that will leave us with a positive 1.00. Now, the question is asking us for the probability of obtaining a mean greater than m equals 22. So when we're talking about greater than, we know that greater than indicates a direction of going to the right. Lesser than indicates a direction of going to the left. We have a positive z-score, so we suspect that it will likely fall right here, and we are interested in getting information that is going this way, because that would be greater than. As we've discussed earlier, whenever you take a z-score and you use it to slice a distribution, in this case it's a sampling distribution of the means, you end up with a larger half and a smaller half. The smaller half is the tail, and the larger half is the body. So in this particular case, which one will we be going with? The body or the tail? You see how I just paused like Dora the Explorer? You guys are already there. We're going to go with the tail. I don't even know why I asked you the question because I gave you the answer. Okay, so once we've determined what we will go with, we will then transition to our unit normal table. And we have a positive z-score, so that means that the tail would be going to the right, and that's the particular z that, that's a particular column, C, that we need to utilize. So let's do that. We will look up z-score of 1. You scroll all the way down and then go back up because I missed it. And voila. We have our proportion in the tail, which is 0.1587. 1587. So the correct answer would be 0.1587. If you were to convert this into a percentage, you would have 15.87%. All right, so I'm hoping that this was helpful. Again, in this tutorial video, I was just trying to present to you a way in which you can transform a sample mean into a z-score and then answer probability questions with that z-score just as you would if you had a raw score that you converted into a z-score. Let me know what you think below, and feel free to let me know what you think in person. Take care.